Hello, in this session I would cover the choice of activation functions. So let's briefly recap what we already understand about activation functions. This is a typical neural network where x is an n-dimensional input vector and w are the weight matrices. So w times x plus bias b gives c1, to which when we apply sigmoid function sigma, it gives a1. Now this A1 becomes an input for the second layer. So it gets multiplied by the weights of the second layer and a bias added to it to give Z2. And to this Z2, when we apply a sigmoid function, it gives the final output A2. And in the supervised learning, we already know the target variable Y. So we can calculate the error function, how much our prediction is away from the desired output variable Y, and from there we can calculate the derivatives of error function with respect to weights and update weights and biases and end up updating weights and biases. So this is the forward feed and this is the back propagation. Now, through our neural network, we are trying to find the value of parameters w and b such that our prediction closely matches the output, which is already known in supervised learning. What happens when we do not have activation function? In that case, if we do not have the activation function, the weights and biases would simply do a linear transformation. The activation function does the nonlinear transformation to the input, making it capable to learn and perform more complex tasks. Basically, it makes the back propagation possible since the gradients are supplied along with the error to update the weights and biases. Without the differentiable nonlinear function, this would not be possible. So let's go one by one through various activation functions. The first one is sigmoid or logistic function. Mathematically, sigma x is defined as 1 divided by 1 plus e raised to the power minus x, and we can calculate its derivative mathematically, and we can finally simplify it to get sigma dash x is equal to sigma x times 1 minus sigma x. This is a very important property because during the forward pass we computed sigma x when we multiplied the inputs by weights and applied the sigmoid function. If we catch that matrix, we can calculate the derivative now with just a few simple matrix operation. We already know this. A few simple matrix operation helps us calculate sigma dash x. This computational speed up is extremely useful when we are doing computations on massive matrices and across multiple layers in a network. Now let's look at the graph of sigmoid function. If we look at the graph, we can see that for a given number n, the sigmoid function would map between 0 and 1. As the value of n gets larger, the value of sigmoid function gets closer and closer to 1. And as n gets smaller, the value of sigmoid function gets closer and closer to 0. And you will also observe the gradient. This red curve is the gradient curve, and the gradient is steepest very high between -3 and +3. Rest of the places it is almost 0, the red color one. And this implies that in this range, -3 to 3, a small changes in x would also bring about large changes in y. And this is a very desirable quality when we are trying to classify the values to a particular class. But there is one problem, and the problem of vanishing gradients. During backpropagation, the weight wij is updated like this. By calculating the partial derivative of error function with respect to partial derivative of the weight, and multiplied by the alpha, which is learning rate, and then if we subtract this value from the weight, we can get the updated weight, which we can again use in the forward feed. Now we have to calculate this partial derivative like this using chain rule, and we can see that in sigmoid function, to the extreme left and to the extreme right, we will have the problem of vanishing gradients. The reason is these derivatives will be very small, and the product of these small derivatives will give a very teeny tiny value for uh, partial derivative of error function with respect to error weight. This would mean that logistic sigmoid can cause a neural network to get stuck during training. Since neural networks use the feed-forward activation to calculate parameter gradients as shown in this equation, and here derivative of error function with respect to weight is the product of all the derivatives calculated at the nodes in the path of output, and the derivatives are very small in case we are at the right or very left. I am repeating it again because it shows that when this value is very small, it can result in model parameters that are updated at a very slow pace, which we don't want, and are thus getting stuck in their current state. The model parameters are not changing at all, they are getting stuck. So how do we solve this problem of vanishing gradient? We will discuss it further in the subsequent slides. There is another second problem, which is the values only range from 0 to 1. Sigmoid function is not symmetric around the origin, and the values received are all positives. So not at all times would we desire the values going to the next neuron to be all of the same sign. Let's change the activation function and see if it solves some of these problems. Let's look at the hyperbolic tangent function, which is mathematically defined as e raised to the power x minus e raised to the power minus x divided by e to the power x plus e to the power minus x. And this is the graph of the tangent hyperbolic function, and this is the derivative. G dash x is equal to 1 minus 10 hyperbolic square x. It solves our problem of the values all being of the same sign. All other properties remain the same as that of sigmoid function. It is continuous and differentiable at all points. The function, as you can see, is nonlinear, so we can easily backpropagate the errors. The gradient of 10 hyperbolic function is steeper as compared to the sigmoid function. Our choice of using sigmoid or 10 hyperbolic would basically depend on the requirement of gradient in the problem statement. But similar to the sigmoid function, we still have the vanishing gradient problem, which can be solved by using rectified linear unit, ReLU. Mathematically, ReLU is defined as a function is equal to 0 for x less than 0 and x for x greater than or equal to 0. So the differential of ReLU will be a step function, 0 for x less than 0 and 1 if x is greater than or equal to 0. ReLU is most widely used activation function, and it can solve the vanishing gradient problem. The sigmoids, if we go back to the sigmoid function, we can see that sigmoid's best derivative was for x is equal to 0, right? And where y is 0.5. But in case of ReLU, the gradient is either 0 or 1, or in a healthy network will be a 1, often enough to have less gradient loss during backpropagation. Experiments show that ReLU has good performance in deep networks. because vanishing gradients happen when derivative of activation functions are very small and tend to 0. Derivative of ReLU is 1 or 0, so it can only vanish gradients if they are less than 0. To minimize problems with gradients, there is patch normalization, gradient clipping, and SALU activation. Let's look at another important improvement, which is leaky ReLU. As we saw that for ReLU function, the gradient is 0 for x less than 0, which made the neurons die for activations in that region. Leaky ReLU is made to improve that thing. And instead of defining ReLU as 0 for x less than 0, we define it as a small linear component of x here in the negative region. So here fx is equal to x for x greater than or equal to 0 and ax for x less than 0. A here is a very small value like 0.01 or so. Differential of ReLU will be fx is equal to 0.01 if x is less than 0 and 1 if x is greater than 0. It is definitely an improved version of the ReLU function. In this case, the gradient of the left side of the graph is non-zero, and so we would no longer encounter dead neurons in that region. Another very important activation function is softmax. It is generally used in the output layer for the multi-classification task, and if these are the logit scores calculated, we apply softmax function to it, we can calculate the probabilities. It outputs probabilities range. The range will be 0 to 1 and the sum of all the probabilities will equal to 1 because here it is normalizing them by dividing by the summation of all the logit scores. The target class will have the high probability. So in this particular case, we can see that it belongs to the first class because the probability here is 70%. So hopefully you enjoyed this session. Thanks for listening.